Welcome back, students. Today we will be discussing about landing performance. So far we have completed takeoff, cruise, endurance. Now today we will be discussing another very important phase of flight, that is called landing of an airplane. And before going to the board, if I try to demonstrate a landing, if you see, this is the airplane and this is the airstrip here. So airplane will align some landmark, maybe the center line of the airstrip, and basically it will be coming like this, and as it comes near the ground, it actually flares up. What is that? It is called flares up. So it is actually putting the nose up and ensures that the rear wheel touches the ground and then starts moving, but same time he applies the brake. Okay? Brake could be of different type. We'll discuss about that. So that whole exercise completes a landing performance, okay, or landing maneuver. But as per regulation, you have to give a specific numbers, a specific guideline for the pilot. And as per that guideline, it is, we start talking about landing performance when the pilot has ensured that the airplane is in the approach at a height of 15 meters, comes like this. This phase is basically, you will understand, is the gliding phase. You will be putting the thrust to bare minimum. Okay? Almost, you can say, ideally it should be 0, but for safety reasons, he may keep some 10-20% on using a clutch. Okay? So it comes like this, the glide like this, comes here. Now it flares up, flares. As it flares, then it touches the rear wheel touches the ground and then applies the brake, and matter is over. What is our aim? Our aim is to find out this distance, which is the landing distance. Okay? As per the regulations, the V15 is taken as 1.3 times V stall and V touchdown as 1.15 V stall. What is this V stall? Remember, V stall is the minimum speed with which I can balance lift equal to weight. But in this case, when I am talking about V stall, please understand this is with flaps on, right? That is, high lift devices are operative now. The flap is deflected by 10 degrees, let us say 20 degrees. So when I am calculating V stall, I should take the CL max value with flaps on. Also, you must understand that V touchdown should be as low as possible to ensure that the impact on the structure is less. Okay? So with this understanding, let us try to find out first this distance, which we call SA. SA means, the notation only tells you that it's the air. So airplane was air till it touches here, till it starts flaring up. This another question comes to our mind. When I'm calculating V stall, what should be the weight? Because for takeoff distance, we have taken the W takeoff, that is full. Airplane with passenger, with fuel, complete fuel. But when you are coming down, landing after operation, please remember that actually the weight of the airplane has reduced. It has reduced by the amount equal to the fuel consumed. Okay? So touchdown estimation, when you are doing, you have to see what is the weight during the time it is now going for a touchdown, which is definitely not equal to the takeoff speed if everything is normal. Okay? And also there is, during this, some CL is prescribed, that also we'll be talking about. Okay? But before I do this computation, please also understand, I'm saying this phase is a gliding phase, right? Gliding, almost a gliding phase, right? What does that mean? You remember, we have studied the gliding flight, and I repeatedly mentioned gliding flight doesn't mean it is meant for a glider only. This concept we'll be using even for aircraft, because aircraft during landing, it has a phase almost like a gliding, where thrust is put to very nominal value. And if this is V, you know, lift is here, weight is here, and drag this side, we are now expert. And this angle is gamma, flight path angle, which is negative, which is nothing but, you see, here. Okay? Try to draw the similarity. In this case, what we learned? I want to come along this line with a constant speed, because I am landing at a constant speed. So in both the axes, there should not be any net force. So what does it mean? It means d minus w, the component of w. So I have here w cos gamma, and I have here w sin gamma. So d minus w sin gamma equal to 0, and L minus w cos gamma equal to 0, right? So this means d equal to w sin gamma, L equal to w cos gamma. You know this. If I combine this, what I get? D by L equal to tan gamma, or I write tan gamma equal to 1 by L by D. Okay? Is it okay? So d by L is tan gamma, so I can write tan gamma equal to 1 by L by D. This is equivalent writing 1 by CL by CD, and you are familiar with this expression that tan gamma is equal to 1 by CL by CD. And if you recall, for gliding, when we wanted maximum range, we want to fly at gamma minimum, and that is only possible if I am flying at CL by CD maximum, that is CL equal to CD naught by K under root. So it's nothing new we are doing. We are using those concepts. But when you are landing, it is not feasible for you to fly at CL by CD maximum. You will be flying at a CL by CD such that, depending upon the distance and all, such that this angle is within 3 to 5 degrees. This is also called glide path angle. Okay? So for that understanding, I have again revisited here. And also to re-stress this point, during this phase, I have deployed the flap. Okay? So CL and CD, they have changed. So I have to be very, very careful during estimation that I should take correct value of CL and CD. This is one. Second thing, in takeoff analysis, we have taken W takeoff, complete weight, fuel, all the airplane passengers. But when I am landing in a normal flight, I should also check how much fuel is consumed. Okay? So that time the weight is not the W takeoff, it is the weight minus the fuel at least. Okay? So these finer points you should know. Now as per the regulation is concerned, the landing distance is defined like this. Once this airplane is at 15 meters above the horizontal, in classically notation wise, you will find regulation use 50 feet. Okay? So from 15 meter, it comes here, flares, applies brake, whatever place it comes to halt, that is the landing distance. And there are specified speed limits that V15, that the V at 15 meter should be 1.3 times V stall, V at touchdown should be 1.15 V stall. Okay? This is to be maintained. Now we will calculate SA and other distances to calculate the whole landing distance. But you could see that conceptually nothing new we are doing. This part we know, gliding phase. This part is a flare. For 3 seconds it will be going at speed equal to V touchdown, which we know is 1.15 V stall. So this also I can calculate. We have done it for takeoff also, similar way. And here we have applied brake. In the takeoff, we found acceleration, took average acceleration, but landing, we will take deceleration, we will take average deceleration, so that we can easily use V square minus U square equal to 2AS and find the S. Okay? Now, how to find this distance? SA is the question. That is a question here. As I told you, in estimating or calculating these things, you have to really apply your common sense to make things simpler, right? And get a quick estimate. That is the most important part. What is done, if you see any book, they have made an attempt to find out different ways. I will be presenting one simple way, and it really works well. And the principle is very simple. The kinetic energy plus potential energy, total energy, retarding force into distance SA. Very approximation, but it works. It's not that bad an approximation, because you can immediately question me, what is this? You're assuming the whole energy is going into this, whole energy is used by the retarding force. Yes, it is exactly not. A lot of other sources are there. The energy is getting dissipated. But major part is this. Okay? So now if I use this equation, what I get? I get kinetic energy half mv square. So it is, I say W by G is m. V square means here V15 square half mv square, so I put by 2. This airplane is also having potential energy here, that is mgh. M is outside, so I have to write 15 gh. Okay, I understood this. This is nothing but, this term will be m g h. So it's m g into 15. What is m? M is W by G. So W by G into 15G. That is exactly W by G into 15G. So it's potential energy. Minus the kinetic energy here, because here potential energy has become 0. So minus V touchdown square by 2. So this is the difference in total energy here. This is kinetic energy plus potential energy at V15 minus the kinetic energy here, and that is equal to the force, retarding force into SA. That is the work done. Okay? By the retarding force, that's the approximation. Okay? If I do this, I'll get something meaningful, and I'll get an approximate value. I repeat, this is not very accurate, but this is not bad, it works. So from here, using this relationship, I can write SA is equal to W by F into V15 square by 2G. Let me write this, V touchdown square plus 15. No issues? You could see that. I have taken the G inside, so V15 square by 2G. This is minus V touchdown square by 2G, and this GG cancels, so this looks pretty good. Okay. Now enjoy the approximation. How these great people have made life so simple and got some relevant numbers. And these do not happen just because of lack of knowledge. This happens because those who have done this approximation and worked in the field, they have experience to really apply their common sense to apply in a manner which makes life comfortable without causing much error. It needs lots of experience, and please enjoy that. Okay. What is being approximated is the retarding force is primarily the drag, and for all practical purpose, lift is equal to weight. Okay. You also understand that lift is not equal to the weight during the gliding. Okay. If you see what we have seen, if this is the gliding, they are coming down. This is W, this is lift, this is gamma, so this is W cos gamma. So L is actually equal to W cos gamma. But here W is replaced by lift. Why? Because gamma, I was telling you, 3 degrees, small angle, small flight path angle. Okay? So it's not a bad approximation. And F is drag, because in the air, the energy is being dissipated because of drag. So this approximation, although not exactly correct, but not a bad approximation. So now I substitute here. So I write SA is equal to L by D V15 square minus V touchdown square by 2G plus 15. This will give in meters. Okay. So that is an approximate expression for your SA, which is the initial part. Okay. Let's again revisit. Please remember, V15 is to be computed as 1.3 V stall with the flaps on, landing gear on, and V touchdown is 1.15 V stall, okay, with flaps and landing gear out. What is also more important, you should understand, when you're talking about drag, then drag means during the air, when it is coming like this, drag we know half rho V square S CD naught plus KCL square, isn't it? But the moment you are putting the landing gear out, the moment you are putting the flap down, it is changing. CL is fine, but because of landing gear out, there is a CD naught of landing gear. Because the flaps are down, there will be increase in drag because of flaps down. So it is a fair enough equation for understanding purpose to write CD as follows. So I can write CD as CD naught plus K CL land, that is CL with which is coming, square, plus delta CD flap plus delta CD landing gear plus some miscellaneous. Okay, you will understand what the miscellaneous soon. Thank you very much.